Thank you for coming to the first Extremes Initiative seminar. I thought I'd say a couple of words about what we hope to accomplish here, and then I'll introduce our speaker. So this event is put on by the Initiative for Extreme Weather and Climate at Columbia University, sponsored by the Executive Vice President for Research and the Earth Institute in Lamont, and we want to thank them for their support. And as I see it, part of our charge is to facilitate conversations on campus between groups of people interested in the theme. Extreme weather events, climate change, impacts, applications, how to use climate information, policy, all of that. And so we're thinking about ways to do that, ways to facilitate conversations. And we've had a couple of events that were on the sort of workshop side of things. We had one just on monsoons in September, run by Michele Biasutti from Lamont. And we thought that it would be good to have some slightly more regular and less lengthy events. I mean, events that only take a couple hours rather than a whole day or multiple days, and that occur with some regularity and try to bring people together for interesting discussions and to hear about things that are going on and off campus. And these are not just for the Columbia community, but for our friends and partners outside. And we have a few people, I believe, here from the insurance industry, from city government, and maybe others that I am forgetting. But at any rate, so this is our first one of these, and we hope to maybe do these a couple a term kind of thing. And the idea is if we serve food, people may be more likely to show up. It costs some money, but maybe it is worth it. And so this is the first one, and this came about because after we had our first science workshop for the Extremes Initiative in May, Radley was one of the speakers, and Eliza, whose last name I am unable to get, Eliza Petkova from the National Center for Disaster Preparedness with Erwin Redlener, and their group expressed some interest in hearing more from Radley about the projections and how they're used in policy and planning. And so we talked about it for a while. Should we do something up at their space or something down here? And then eventually we thought, well, let's have a seminar series, and this is a good thing for the first one, because I think the work that Radley does fits right in our theme, and right from the beginning we had interest from different groups who don't normally talk to each other, so that seemed auspicious, and so here we are. Welcome and thanks for coming. And now I will say a few words about Radley Horton, who's come all the way to us from NASA GIS, several blocks away. But he's an associate research scientist there at the Center for Climate Systems Research at Columbia, affiliated with NASA GIS. And his research interests include sea level rise, extreme events, Arctic sea ice, and climate adaptation. And we have time, so I'm going to tell you some of the many, many high-profile activities he's involved in. He's a convening lead author for the third National Climate Assessment, the Northeast Chapter, the lead PI for the NOAA Regional Integrated Sciences and Assessment-funded Consortium for Climate Risk in the Urban Northeast. He's the Columbia lead for the Department of Interior-funded Northeast Climate Center and an NSF-funded Climate Change Education Partnership Project. And he's also the deputy lead for NASA's Climate Adaptation Science Investigator Working Group, which is charged with linking NASA's science to its institutional stewardship. He's been a co-leader in the development of a global research agenda in support of the UN Environmental Programme's Program on Vulnerability, Impacts, and Adaptation initiative. And he serves on numerous national and international task forces and committees, including the Climate Scenarios Task Force in support of the 2018 National Climate Assessment. And he also teaches here in our Sustainable Development Program. So his title, as you can see, is When 1 + 1 = 3, which is not bad math, but is about how to think about multiple hazards at the same time. And so he's going to talk to us about climate and policy and how they should work together, and hopefully we can all think about how we can have some more interaction and discussion on that theme. There will be time for questions after. We have the room till 2, so please stick around, have some cookies, and enjoy. So thank you, Radley, and welcome.
Great. Thanks, Adam. It's great to have the opportunity to be here with everybody. My talk is going to be fairly wide-ranging. I'll try to sort of quickly go over some of the activities of our group at Center for Climate Systems Research. But I'm really excited by this theme of collaboration. I've had the chance to work with so many climate scientists in the room, and increasingly risk management experts, people from the Sabin Center, and I think that we can use this topic of extreme events. It's a really logical sort of place for us to expand collaborations in a way where we can mix really exciting and cutting-edge science with very decision-relevant, impact-relevant topics as well. And I'm really excited to get to say that 1 + 1 = 3 as well. Okay, so one thing to sort of start with is how do we want to define an extreme event? So a little bit of jest here, but obviously a senator bringing a snowball onto the Senate floor points to big issues, points to potential big winners and big losers when we think about vulnerability in the future and some of the issues that extreme events help to bring right to the fore. Increasingly, we're seeing climate scientists becoming much more engaged, speaking up and sort of joining in the policy process. And maybe we can talk a little bit about sort of all of our reflections on that if we have time in the discussion. Okay, but sort of more seriously, what we'll talk about here is we'll do some definitions of extreme events. I'll quickly talk a little bit about the approach that our group has used historically when we do risk assessment focused on extremes. And then I'll point to some of the things we're doing in our group here at Columbia and that are being done more broadly in the community to push the science a little bit further, to really start to uncover, for example, some of the processes which drive key extreme events, thinking about some of the ways that different climate variables interact together and may be correlated with each other, how that can change our perceptions and our characterizations of risk of certain types of extremes. We'll also talk about some of the impact analyses based on extreme events that we've worked on in our group. And I think have time for some discussion of science policy interactions as well. I'll focus a little bit on some of our work with New York City especially. That's really gone on now for about 7 or 8 years, and I think has some nice points to mention about the ways that the policy has really supported and pushed the science forward from the beginning. And I think hopefully that can lead to a nice discussion as well. Okay, so what are some of the characteristics of extreme events? I mean, clearly, obviously, this implies something that's unusual in some sense. Extreme events operate across a very broad spectrum of spatial scales and temporal scales. This is everything from a very small thunderstorm that might sort of spring up with a minute's warning, a tornado that might very briefly touch down, leading to devastating impacts over a small area. But we can also think about the extreme event timescale as extending out to decadal periods, for example, decades of drought conditions. And arguably, depending on how you'd want to define extreme events, we might even think about centennial timescales. You could make the case that if you're doing, for example, a sea level rise assessment, an extreme event for you might be a gradual but sort of irreversible undermining of an ice sheet on a timescale that might be multi-century. So I think, we'll want to think about interactions across those scales. Obviously, there's a lot of different spatial and time scales where we could sort of engage around these issues. As I mentioned earlier, a lot of extreme events are multivariate. Drought is a combination of precipitation and temperature and other factors. We'll go through some other examples of how different climate variables and sometimes societal variables too can influence how we define an extreme, like drought, for example. And they can have many causes. So as we start thinking about attribution of extremes, it gets complicated in a hurry. All right, so this is fairly obvious. Why do we study extreme events? They impact the things that we care about most fundamentally. I had the chance with some of our work to go to Myanmar for a World Wildlife Fund project earlier this summer. It's estimated that 180,000 people died during Cyclone Nargis in 2008 there. People die, there's economic loss, and for the people who are left behind, especially in very vulnerable communities. Recovery, if it happens at all, can take decades. So, clearly this is an area where Columbia can contribute from a variety of ways, not just the climate science perspective. I think a related point is how a better understanding of extreme events can improve decision making as we're thinking about adaptation strategies, building a flood wall, whether or not to build a new reservoir. Do we have a clear sense of how we define the recurrence period for a certain type of extreme? These are going to be critical issues as we see more and more money being spent on adaptation, and potentially some unrealistic assumptions as the next set of extreme events occur after those adaptations are put into place. So maybe we can anticipate some of the challenges, some of the climate science asks that we may increasingly get as adaptation strategies are more and more put into place. Obviously, there's a much broader science of evaluating adaptation, but I think climate science role in evaluating adaptation strategies is going to be an interesting area going forward. And then more generally, extreme events present a lot of challenges and opportunities from a science perspective. Actually, the other thing I wanted to say is that extreme events are really exciting scientifically. I think for a lot of us, it's okay to say that we're very passionate about learning more about the basic sort of physics of how some of these extreme events occur. A lot of them operate on timescales that aren't captured by climate models. If they're very rare, we don't have much of a historical record many times to look at. So there are a lot of really interesting challenges, even before we start to ask how climate change might shift the nature of some of these extremes. And they're also viscerally exciting. This graphic on the bottom here is showing a storm chaser who was killed in 2013 tracking a tornado. So we're drawn to these events. They present challenges and opportunities clearly from a science, policy, and communication perspectives. More and more from the legal case, we're going to see the loss and damage community wanting to focus more on individual extreme events. Is there a signature associated with climate change? Are there particular actors who potentially could be held accountable for their contributions to individual or series of extreme events? Arguably, that's looking more and more like a possibility. From a communications perspective, extreme events can really move the envelope as well, as we saw after Hurricane Sandy, this idea that there was sort of a teachable moment. Whether or not Sandy could be linked in many clear ways to climate change, it may have offered an opportunity to get people sort of thinking and have more and more a dialogue about our vulnerabilities to climate, which in a lot of ways naturally gets you to thinking about climate change, independent of whether an individual event can be linked. And there are a lot of communication challenges as well. So here's a graphic just to sort of bring home this point about how devastating recent extreme events have been. This is monsoonal flooding this past summer in Myanmar. It's leading to the posing of a lot of really challenging questions. How much of this flooding can be linked to environmental changes? Not in the sense necessarily of changing the amount of rainfall, but deforestation in forests, in some of the large existing forests. Is that making flood events worse? Difficult question to answer for a variety of reasons, but one of the pieces clearly is trying to assess what's a normal and what's an extreme year from a heavy rain perspective before and after climate change. Very challenging, but an example of how policy questions are increasingly being asked. Okay, so here's a list, probably too small to read, of all the billion-dollar extreme events from 2014. There's been some upward trend in the number of billion-dollar extremes, even when you account for inflation. All right, so now let's shift gears a little bit and go to sort of the second phase of the talk. Here's where I want to talk a little bit about the approaches that we've used in our group historically, going back 5-10 years or so, I would say, to focus on risk assessment around extreme events. Things like the frequency of a hot day above 90 degrees, things like recurrence of the 1 in 100 year coastal flood event or a heavy rain event. So some of the characteristics, I would say, of the sort of historical approach to this type of risk assessment has been, one, to focus on shifts in mean or average conditions rather than trying to really analyze what might be happening at the tail of the distribution, whether the nature of the really hot days could change more than the nature of the sort of average day in summer, for example. A lot of those historical assessments, I would argue, maybe weren't process-based. They were a little more inclined to just take outputs from a climate model, for example, or look at historical data on, whatever it might be, heavy rain events, without maybe going in detail into trying to identify some of the processes that fueled those events, how those might change with climate change, and whether climate models are able to capture some of those processes. And I think it's also fair to say that a lot of the historical assessments were single variable approaches. You'd consider what might happen to temperature, then you'd consider what might happen to precipitation, but you didn't necessarily consider how they'd interact with each other to change risk. So this schematic is probably one that everybody's seen before, I'm guessing. So this is your historical distribution before climate change of temperature. For New York City, you'd have a lot of days that were sort of in a 50 to 60 degree range, a few days below 15 degrees or so, or say above 95. So if you take sort of the simplest approach to risk assessment and go to climate models and ask to first order, what do we think they can probably do the best job on, you start with the sort of average changes in temperature as opposed to the specifics of very rare events. And I think it's important to emphasize that just shifting the average alone, just having all the temperatures go up by, say, 4 or 5 degrees by mid-century can have a huge impact on how frequently you get that rare tail event. It can turn that 95-degree day, or for New York City, it can turn that 90-degree day into something that's happening 3 times as often by mid-century. If we do the same type of analysis for mean changes associated with sea level rise, we reach the conclusion that about 2.5 feet of sea level rise, the mean change in the ocean height, 2.5 feet of sea level rise, by the way, is a high-end projection for mid-century. But by the end of the century, it's a very middle-of-the-road projection for sea level rise, 2.5 feet. If we don't change storms at all, if hurricanes don't get stronger or more frequent, nor'easters don't change at all, just that shift in sea level of 2.5 feet will give you a 5-fold increase in how often you get the 1-in-100-year flood event. It becomes something you expect once every 20 years. So before we delve deeper into how the tails of these distributions might change, whether storms will change, whether atmospheric patterns will change in a way that shift the tail of the distribution in those hottest days more than average days, it's important to emphasize that just shifting the averages alone can be a game changer for a lot of systems. But that doesn't mean we shouldn't try to go further and ask the question of whether the variance might change on some of these variables. Okay, so just a schematic on the sea level rise example. I think we can skip this in the interest of time. The point just being that a small amount of sea level rise can give you much more frequent coastal flooding and obviously a much bigger area flooded when a storm comes along. And it's been estimated in the Sandy case that 80,000 additional people, I believe, in the region experienced flooding than would have if Sandy had hit basically 100 years ago when sea levels were about a foot lower. Okay, and here's that graphic showing how 2.5 feet of sea level rise, which is the high estimate for the 2050s, turns what used to be the 1-in-100-year storm into a flood level that's experienced 5 times every century or once every 20 years. Okay, so now, getting into a little bit of the newer research, I'll show a few examples. The first is a paper that we put out earlier this year in GRL. And basically the bottom line to emphasize here is in this paper, we looked not just at how the average summer temperature will change in the 2050s in regional climate models relative to today, but we honed in on what's the expected change in the warmest day per year. And so what this graphic is capturing here is, so this is a summer analysis. That's your change in temperature for the hottest day per year. So you go through a set of regional climate models, ask what's the temperature that occurs once per year in a base period centered around the 1980s, compare it to the temperature that occurs on average once per year in a decade centered around the 2050s. So that number can be compared to just the average of all the summer days in the base period of the 1980s as compared to all the summer days in the 2050s. So if we look here, we see the difference. We see that summer average temperature change subtracted from the amount of warming you're experiencing in the future on those hottest days. And you can see a pattern emerging where you have more warming in large parts of the Northeast on that hottest day than you do in the sort of typical summer day. And you can do the exact same analysis for the coldest occurrence, the coldest minimum temperature in winter. For the typical winter day minimum, averaged across all the winter minima for the 1980s as compared to the 2050s shown here, versus what's happening to that coldest night per year, future relative to base period. So in this case, you see not just over the east, but over large parts of North America, that extreme winter temperature warming much more than the average nighttime winter temperature as shown here. Oh, does that work? All right. Okay, we'll keep going with this. Thanks, though, Felix. Okay, so what if we try to express this in terms of recurrence? How much does it matter that we're seeing those extreme winter and extreme summer temperatures warming more than the just summer and winter averages? So let's just hone in on a particular example here. We did an analysis of historical daily data from Baltimore. We can just focus on these top two rows here. So if we look at the base period, the 1 in 10 year extreme heat event for Baltimore was about 103 degrees, right? So that's a temperature that's going to be associated with big increases in mortality. It's presumably going to be a temperature that's associated with a greater risk of power failures if those heat events are lasting for a fair amount of time. It's going to have impacts on infrastructure. It's going to be associated with bad air quality. Major event, especially for vulnerable populations. So if we use the sort of historical approach of just saying how much are the summer average temperatures going to change, if we apply that uniform average amount of summer warming, we see a big change in that recurrence, something that used to happen once every 10 years, happening 3 or 4 times per year by the 2050s. If we use this alternate approach where we look at the change in the hottest days, which was greater for Baltimore, you see about 50% more days crossing that baseline defined extreme temperature of 103. So, you could argue that's a significant increase, 50%, but given the uncertainties and relative to this huge change we observe in the mean, I think it's maybe debatable how much extra value you're adding. Certainly what you'd want to do next, and what we did in the paper, is try to look at the processes that are associated with those extreme heat events in the observations. Are those models able to capture some of those processes? You can do the exact same thing, of course, on the cold event side. The once per year, in this case, minimum temperature for Baltimore, about 3 degrees. As you get out to the 2050s, if you have average winter temperatures increasing, you see that occurring about 70% less often. If you go to that really extreme warming of the coldest days, about 90% reduction in that extreme temperature. And as we'll see in a little bit, that's going to have a lot of impacts too, not all positive probably from an ecosystem's perspective, having few of those extreme really cold events. Okay, so now the next example I want to show is one where we go a little deeper into looking at coastal flood risk. And what we'll see here is an assessment that pushes beyond the approach of just looking at how mean sea level rise is going to impact flood risk, but starts to explore how we might see storms changing as well, and specifically what might happen to tropical storms. And then there's an added piece where in that analysis we looked at correlation across climate models in the piece associated with sea level rise in that model with the tendency for stronger hurricanes, more warming of the upper ocean in places that tend to favor stronger hurricanes along the East Coast. So this next analysis is going to include really looking at how extremes might change, in this case hurricanes, and looking at that joint risk of sea level rise and changes in hurricanes. Not just treating each of those two things separately. If you treat each of them separately, you'll get a really big increase in flood risk. But if you consider correlation across the terms, you could potentially see a different pattern based on the correlations, for example, between the models. Okay, so just to go through this real quickly, this was a paper in Nature Climate Change in September. So from the sea level rise perspective, there's a climate model-based study. So we can't capture all the sea level rise terms using climate models. They can't really tell us anything about the land-based ice sheets. We're just using the climate models from a sea level rise perspective to tell us about the sort of overall thermal expansion of the ocean and also the regional patterns of sea level rise, right? Because sea level isn't uniform across the ocean. And then on the element of trying to look at how storms may change, we're basically just using PDI, so just comparing sea surface temperature anomalies in this sort of generation region in the tropical North Atlantic as compared to sea surface temperatures across the tropics. And then to estimate changes in flood risk, frequency of flood occurrence, we look at the historical tide gauge data for these 5 spots along the East Coast that have a long record. So I don't have time to go into the details of it, but what I wanted to highlight, first of all, is that simply considering the climate models overall suggest an increase in the strongest storms. If we just use this simple metric of PDI, there's a lot of other things that could influence hurricanes and their track. But if we just look at PDI, the models suggest an increase in risk. So if we combine that with the sea level rise risk, which we already saw, by itself will give us more frequent coastal flooding. Putting those two together can already get us past 1 + 1 = 2, if that makes sense. But if we also look at this issue of correlation within the models, so if in each of these GCMs we plot, so each of these numbers here represents a GCM. On the left, you're seeing the RCP 2.6 scenario, basically greenhouse gas concentrations essentially staying where they are right now, versus the RCP 8.5, arguably the trajectory that we're on. Each GCM here represents a combination of change in sea level within that GCM versus change in this proxy for hurricane strength into the future. So the majority of the models cluster, we can just focus on the RCP 8.5 case, in a state where you have some increase in sea level as we'd expect and some increase. So baseline risk here is actually expressed as a 0. So you see a lot of models increasing that hurricane risk. But what's interesting, not necessarily decision relevant, but I think interesting as an exercise, is that there's this group of 3 GCMs that have this combination of a high correlation of more sea level rise than the other climate models would suggest, and this large increase in risk of really strong storms. So, we're certainly not there in terms of saying anything about whether these models are any better than the others. There's probably no reason to think they are. I really want to just sort of use it as an exercise to show how, as we're moving forward, you could think about this joint risk across models, across places, across time, as a way that you could really sort of shift that distribution. If you're approaching climate hazards from a risk perspective, thinking about joint risk and correlation can have a big impact on your results. And under some of the more extreme scenarios in the study, we're seeing something like a 100-fold increase in this flood index. So these kinds of correlations can matter, even as they're not necessarily decision relevant at this place. But if you were, for example, representing an interest that is really sort of a fail-safe, a nuclear power plant along the coast, you could make the case that from a risk management perspective, you'd at least want to consider some of these extreme outcomes with much higher risk than you would arrive at if you just separately considered sea level rise or separately considered what might happen to tropical cyclones, even as they are by definition very low probability events. Okay, so now the last example I want to give of some of our ongoing work now where we're trying to push some of the science a little further is a case where we've gone beyond looking at just what's going to happen to high temperatures to explore the relationship between high temperatures and humidity. So this is a paper that led by my graduate student Ethan Kofel. We're going to be submitting this this month. And basically, the idea is to focus on wet bulb temperature, which combines the high temperatures with the humidity. So in some of the recent heat waves that have gotten so much attention earlier this summer and going back to some of the major events, for example, 1995 Chicago, 2003 Europe, 2010 Russia. In general, none of those events have had a wet bulb that exceeded 31 Celsius or so. Now, it's been estimated, Sherwood and Huber, for example, that 35 Celsius for this wet bulb temperature is kind of a theoretical max for human tolerance. There's a lot of literature that suggests that you'd start to see really big impacts much below that 35 Celsius. This is sort of your ideal conditions in terms of the body being able to ventilate itself. No exposure to sunlight, no clothing, for example, blocking the body's ability to cool itself. Probably you'd actually start to see major human impacts much below that wet bulb of 35. So we'll sort of quickly go through and look at some of these findings from this work. So before we look at the wet bulb projections, I wanted to contrast by showing what happens to this estimate of heat risk and heat stress risk if we just look at temperature alone. If we take a traditional approach, just looking at temperature, what do you find? So what you're seeing here is a summary across, I believe it's 11 climate models, bias corrected. So for a base period from 85 to 2005, you're basically seeing what the once per year temperature over that 20-year period, base period, would be on the left. On the right, you're seeing, as we move forward into the future, how often, how many days per year is what was a once per year event in the 1980s occurring. So the first thing that jumps out is, in a lot of tropical into mid-latitude regions, big increases in that frequency of occurrence, right? Just shifting temperatures alone are going to give you 30-fold increase or more, in some cases up to 70, 80 or more increase in the number of, so you're getting to 70 or 80 days per year instead of one per year, just by shifting temperature alone. So that's a huge impact. But keeping in mind the idea that this wet bulb temperature is much more relevant in principle to human survival because it directly speaks to the body's ability to cool itself. Whereas with really high temperatures, if the humidity isn't high, the body, at least under ideal conditions, is going to be able to cool. But if the wet bulb temperatures get really high, it implies a fundamental limitation on even a perfectly healthy or extremely healthy person's ability to cool themselves. So what happens if we look at this exact same figure, but instead of showing the once per year temperature on the left in the base period and the frequency of occurrence of that temperature in the future, let's look at the exact same thing for these wet bulb temperatures. So on the left, as I just said, the once per year wet bulb temperature over a base period. And then as you get out to the future, what happens to, how often are you getting that same extreme wet bulb temperature in the 2060s? So if we toggle between these, we can see that there's a much bigger increase in the frequency of occurrence of these high wet bulb temperatures than there is the frequency of occurrence of that once per year temperature extreme. So here you're seeing essentially, the vast majority of the tropics, 70 or 80 events per year exceeding that once per year in the base period. And we can hone in on a few regions. Obviously, with this kind of work, you don't want to focus on the specific numbers. You don't want to focus on the specifics of the spatial pattern. This is solely an effort to identify sort of first order of magnitude, an area of concern and somewhere that I think is worthy of more research. So with that caveat, again, don't focus on the specifics of the grid box or the numbers, but this is just zooming in more detail on that last figure on the right. Parts of coastal India, parts of coastal Myanmar, over 100 occurrences per year of that extreme wet bulb temperature that happened once per year in the base period. And even over parts of the U.S., Southeast U.S., the current once per year happening something like 40 or 50 times per year. So that, of course, implies not just more frequent occurrence, but longer duration of these high heat stress events, less ability for people, infrastructure systems to cool off in the evening, to some extent additive hazard with longer exposure. It's not just going to be more days, it's going to be longer exposure when these things happen, fewer opportunities to seek respite. Okay, so this is still just recurrence based on that once per year in the base period. What if we try to actually move into absolute terms, talk about real wet bulb temperatures? So here you see the once per year wet bulb temperature in the future, in the 2060s from these models. So now you're seeing once per year in the 2060s on average, very populous areas of India, China, having a once per year wet bulb temperature around 31 degrees Celsius or so. Again, don't focus on the specific numbers. The issue is just to sort of highlight growing risk. And even over much of the U.S., starting to see every summer wet bulb temperatures projected to occur that are as high as basically what's ever been experienced in these areas. And if we want to translate this into vulnerable populations, we can look here at how many people per year in various parts of the world are projected to be exposed by decade, 2020s, 30s, out to 2070, to 31 degrees Celsius wet bulb temperatures. Now, there is a population projection added to this as well, using one of the SSPs. But the majority of this change, the majority of this growing risk, comes from the higher temperatures and the joint risk of the high temperatures and high humidity. So these are big numbers. I don't know if people can see them, but this is 500 million people. Yeah, the numbers are right up there. 550 million people in that 2060s decade, whereas the vulnerability in the 2020s is sort of in the 150 million range. And again, it's primarily driven by the warming, not by the population projections. And if instead of focusing on a few regions, we look at the entire globe and consider higher wet bulb thresholds, you can see the patterns here. So the 32 degrees Celsius wet bulb temperature affecting about 700 million people by the 2060s in the typical year, and the 33 degree Celsius affecting 250 million people. And this is really an emerging risk. You can see here, the base period. This is essentially not happening. If we wanted to decompose, how much of this change is due to the increase in temperature versus population, you can see that number here. So the vast majority of it is coming from the warming you get if you were to keep population constant, as opposed to the population increase you'd get if you kept climate constant. And if we go to 34 Celsius, which I think, probably indisputably a major risk, this analysis suggests 50 million people a year. So even that's a big number. All right, so a few conclusions about this study before we shift gears. Significant annual exposure, obviously. Some of the events that are very rare today become annual events globally. And this is going to impact essentially everybody, anybody who works outdoors, if these projections come to pass. It's a physiological limit. Okay, so let's talk a little bit about impacts now. I thought I would quickly survey a few things that we're doing that maybe point towards less appreciated impact, but areas that we think are just sort of emblematic of all the different types of impacts we're going to have to think more and more about as we see more frequent occurrences of some types of extremes. So this is a paper that Ethan led earlier this year where we looked at the impacts on the aviation industry, and specifically takeoff weight restrictions for airplanes due to extreme high temperatures. So the figure in the top left there is showing LaGuardia Airport by decade, the frequency, the number of days per year when you have a weight restriction. Basically, when your air temperatures are so high, given that short runway, that planes are forced to take off with less cargo or less people than they were, in some sense, designed for. There's an imposed weight restriction. So the blue bars show the base period, essentially 1980 to 2010, and you can see that there's some occurrences in the base period. But as we get out into the future with this warming, you're going from something like 20 days per year to more like 70 or 80 days per year when you're having, in this case, a 10,000-pound weight restriction, which works out to about a 20% reduction in passengers or cargo required as you get out mid-century on something on the order of 1 out of 5 days. So one other quick example of impacts. This is some work that Corey in the audience is leading for us. Looking at the southern pine beetle. So this has caused a lot of damage for a long period of time in the southeastern U.S., on the average of 200 million per year in tree damage. It's been a major forest pest for decades or longer. It was first seen in southern New Jersey around 2001. Since that time, in the last 15 years, it's made the jump, a lot of it just in the last year or two, into Connecticut, eastern Long Island, and more recently, I think in the last year, up to even parts of mid to northern New York State. So there's an issue about whether those populations will become established or not. But this got us, and there's some literature suggesting that the northern extent of the species is very much driven by what I alluded to earlier, those really cold nighttime temperatures. Not the average temperature in winter, but that sort of coldest night per year. When you get that really strong cold temperatures, the species can't survive. If you don't get that really cold temperature, it's able to make it through winter with a population that has then more rounds to reproduce, and you can see this sort of jump in the behavior. So we don't have time to go into the details here, but there's an overlay here showing the 3 different types of pine forest, and basically when we use a set of global climate models, what do we see as the year of emergence? When do you stop seeing those temperatures that you currently have that kill the species off and knock it down? As we get out into the future with fewer of these extreme cold temperatures, the species is able to be viable by the time you get out to the 2040s, as far north as really up into the Canada border. So if we had time to go into the details, we could talk about all the caveats. But really, this is just, as with the earlier studies, just an effort to sort of illuminate a potential vulnerability, that there is a real sensitivity to temperatures. And this is a physiological constraint on the species. Okay. I think largely just for the purposes of discussion, maybe, I thought I'd sort of quickly do a little recap of detection and attribution issues. Probably we'll have a talk, I bet, on that at some point soon, but maybe I'll just sort of put a few ideas out there, and maybe that can get us into a little bit of a discussion. So we're circling back here to major extreme events globally from 2014, delineated with these categories. And so those of you who've been sort of following this literature, this is an area that's really taken off. A lot of scientists within Columbia have been at the cutting edge of a lot of this work. Focused on really the extent to which we can attribute when a single extreme event occurs. What can we say about whether climate change has increased the risk of this type of event relative to, say, baseline or natural variability? And the most recent report, the 2014 report in BAMS, came out last week, was it? So maybe we can discuss some of that. So some of the science challenges here when we sort of invert, and instead of asking how do we think a type of extreme event will change in the future, will really cold events become more common or less, this is a little different approach where we're really sort of in one sense aiming for greater precision, honing in on a particular event. Can we say whether this has changed due to climate change? If we can't say, and part of that of course is saying how have the drivers changed? If we're talking about a hurricane like Sandy, can we say if sea surface temperatures are one of the factors that drive those hurricanes, have we seen a signal in sea surface temperatures that we can attribute to climate change? But obviously there are many, many drivers for everything from a drought to an event like Sandy. Unpacking the links to a change in climate is really challenging. And by definition here, we're talking about really rare events. So we have to sort of keep in mind that we don't have a good sample size, a good handle of the natural variability. If we're trying to talk about a 1 in 100 year event and we have only a 100-year historical record, by definition we can't really fully sample the risk. And you add on top of that the idea that there could be cycles of natural variability that are longer than, say, 100 years that, separate from the sort of small sample size issue, there could be low frequency variability as well. So this is just a couple examples of how you can have very different perspective. These are op-eds on the California drought, one from 2015, one from 2014, very different perspectives. Now, to some extent, this can be as simple as how are you defining your extreme event? Are you defining a drought as an absence of precipitation, or are you defining it in a more integrated way that considers impacts of higher temperatures, what they might mean for evaporation, what they might mean for your snow reservoir during your critical being able to sustain you during dry months, what it might mean for water usage as well. So I thought I'd just sort of put up these three elements I think often go into extreme event attribution. And I think depending on how much you emphasize each of these three factors, it can have an influence on the role that's perceived of climate change in sort of driving some of these risks. A lot of types of extreme events happen on spatial scales that climate models can't simulate. But for some types of extremes, there may be large-scale patterns associated with them, which we think climate models can do a pretty good job of. So in those cases, it might be very useful to run a long-period climate model simulation for a historical period with baseline greenhouse gas concentrations, and then run the same simulation in the future with higher greenhouse gas concentrations. Do the models suggest more frequent or less frequent occurrence of that type of setup at the large scale that's associated with an extreme, right? So this could be high pressure off the coast of California associated with drought conditions. This could be a steering pattern that's associated with storms like Sandy making more of a turn towards the left, for example. We're drawn ideally to looking at observed trends in variability. But as I said earlier, some of the extreme events we care most about are so rare that the observed record can't help us that much. One thing that's gotten a lot of attention is a less rare type of event. At the last National Climate Assessment, one thing that got a lot of attention is these really heavy rain events over much of the Northeast, a sort of 1% occurrence, which is essentially on the days when you have rain, if you capture those days that were sort of the 1% of the wettest, 1 out of every 100 of those days. If you look at the whole Northeast over the last 55 years, you had about a 70% increase in the amount of rainfall that was happening in those really heavy rain events. That certainly matches theory in the most general sense. Warmer atmosphere can hold more moisture, sea surface temperatures are going up. But it's actually really challenging to try to unpack how much of that trend is due to climate change versus natural variability, because if we're focusing on those extreme events, there can be huge decadal variability. So depending on how much emphasis you put on each of these three categories, that can be a big driver in the extent to which you see a climate change signal in recent extreme events. So I think I'll leave that piece there, and maybe in the discussion, folks who've been more involved in some of these studies can weigh in with their thoughts. So I thought in the remaining time, I'd sort of circle back, speak a little bit to some of the things that Adam talked about, sort of comments on science policy, interaction, some of the challenges, and then maybe a few ideas for where we might go with some of this work in the future. So I wanted to highlight first this example of a science policy interaction that I think has been very, very successful, going back really to about 2007 or so. Scientists at Columbia and elsewhere have been working with New York City's government to incorporate climate risk more and more into their planning. So, if you go back to 2007, that was when Bloomberg first introduced Plan YC. Initially, it had a big focus on greenhouse gas mitigation and emissions reduction. Under the leadership of Cynthia Rosenzweig and others, there was really a push to get adaptation on the map at an early stage in New York City's planning. And as early as 2008, we started working on the first assessments of how temperatures and sea level might change for the city. And you can see initially that, all along it hasn't just been city government. There have been these agencies within New York that are well-funded, DEP, for example, that have really helped push forward some of the science tailored to their particular concerns. For DEP, this was the Water Authority. This was things like what's going to happen to turbidity in the reservoirs in the future. If we have more heavy rain events, is it going to have implications for water treatment for this, the only really big system of its kind in the world that currently isn't treated. Everything from that to how will heavy rain events in the cities increase runoff and fouling of coastal waterways. So a lot of that interaction predated Hurricane Sandy, and New York City, had an adaptation plan going into Sandy, and some steps had been taken. And in fact, I think just weeks or maybe a month before Sandy hit, it was basically codified into a local law by the city council that climate projections should be updated every 4 to 5 years and built into city planning. So that was sort of the New York City piece, but there have really been a lot of other associated examples across the Northeast. I'd say there's been a lot of proactive planning around consideration of climate risk. You can also see some of the projections of New York City's panel on climate change being built into federal planning efforts. So coordination across FEMA, for example, NOAA and the Army Corps of Engineers, a sea level rise viewer, and really the ultimate objective is to build in planning for sea level rise into FEMA projections and these 1 in 100 FEMA maps, these 1 in 100 year storm surge maps that are really fundamental to a lot of zoning and mapping decisions. Just last week, New York State's DEC adopted the sea level rise projections of New York City Panel on Climate Change for their efforts going forward. So these are some of the groups that have engaged with New York City Panel on Climate Change, with the climate science. And I wanted to sort of say a little bit about, from my perspective more generally, what are some of the things that tend to make these collaborations work. I think it helps a lot if the background vulnerability to extreme events is high. That tends to be the case just about everywhere. I guess you'd say unfortunately, but fortunately in some ways. So even if there wasn't a strong link between climate change and some types of extreme events, if you have that high background vulnerability to coastal flooding, to extreme heat events, if your systems aren't well adapted to deal with some of those types of extremes, if you have large vulnerabilities, it's easier to get that buy-in. It's easier to sit down and have those conversations where you ask decision makers, what are the weather events that impact you today? What are the things that keep you at night? What are the keep you awake at night that are your sort of big fears in terms of ways your system could be damaged, ways your mission could be compromised? And then, I think, the successful interactions, if you have a strong signal about how that hazard might change in the future, well, that, can be transformative. I mean, New York City, I think, basically has accepted the premise that even if storms disappear, which isn't going to happen, sea level rise projections, even sort of middle-of-the-road projections, suggest that by the 2080s, the coastal flood risk is going to go up dramatically. Additional areas are going to get flooded. It's not seen as controversial at all. And again, since you have that background vulnerability to begin with, it's easy to, it certainly doesn't guarantee action, but it's a good sort of first step towards that. The leadership role is huge. When Bloomberg convened these task forces, he attended the first meeting in person. He sent the message to all the commissioners that this was something he cared about, something they needed to report back on. The risk management framing was huge. The city didn't have to sort of weigh in on what they thought was the single most likely amount of sea level rise or temperature change. It was a flexible approach. If you were designing for a fail-safe piece of infrastructure that's going to needs to last for 100 years, you look a little further out on the curve into a maybe less likely but high consequence scenario, such as a more extreme sea level rise scenario. But I think New York City had a strong foundation, to say the least, in that kind of risk management and probabilistic thinking. So there wasn't really an obstacle when climate scientists start saying that some of these pieces are uncertain. That's something that you basically say, of course, yeah, we get that, but give us the information you have, and let us know where you don't feel that there's enough confidence to give a quantitative projection as well, and we'll try to figure out a way to deal with that. Funding for adaptation is what I was referring to here with this next bullet. There's so many places, obviously, around the world where you just don't have the resources available or the political will in many cases to deal with some of these growing threats. That's less the case in New York City, which you can argue increases some of the moral hazard issues for the city and for other regions. But again, it's sort of a precondition to getting more action. And I think in some ways the most fundamental piece is this iterative science policy maker interaction piece. From the beginning, before we did any climate projections for New York City, we were sitting down with those work groups, a transportation work group, a communications work group, an energy work group, asking them, what they were worried about. What's their time scale that matters to them? Do they want to know the most likely projection for number of days over 90, or do they want to know a sort of worst case scenario for days over 95? The issues they raise, how do they want to see the information? Do they want a 2-page tear sheet that gives a sort of central range of most likely projections, or do they want qualitative information about what we should be sort of tracking going forward as we try to identify some of the limitations of the science and where the projections are most likely to be wrong if they're wrong? So by doing that kind of co-generation from the beginning, it made the science better. We had the buy-in from the stakeholders, and I think this is part of why I think that the cities, the agencies, the countries that are taking this approach are going to be in a little better position as we get to sort of a new phase where a lot of adaptation is underway, a lot of money is being spent, but we're much less far along in terms of asking questions scientifically about what success might mean. Are these projects defining what a successful adaptation might be? Over what time scale? What are the benefits that might go with the project? What are some of the potential costs? Is it being implemented on time and at cost? There's a whole new science driven, as much by decision makers as scientists, I think, around evaluation of some of these adaptation strategies. So, I don't have any particular insights on the converse or inverse of this. I mean, some of the challenges in science policy interaction are, many places around the U.S. and elsewhere where the science can easily get caught up in the politics of climate policy. And that of course, doesn't have to be on a sort of contrarian or denialist side. There can be issues of the sort of policy getting too far out in front of the science. Scientists obviously need to be careful how they represent the science in all contexts. Coordination, some regions, parts of the Northeast, for example, where there's a lot of well-meaning efforts to do more around adaptation are running into challenges of is there coordination of these strategies? And is an adaptation in one place going to have a negative impact? Is it going to lead to more flooding outside of that region? As one example. Who's going to pay for the big scale adaptations or adaptations working at cross purposes? There was money not being spent efficiently or sort of where it can have the most impact. The challenge of implementation, I think this is huge and underappreciated. And as I said earlier, how to evaluate adaptation strategies that are underway. Should a plan to evaluate an adaptation be built in from the beginning to a HUD proposal or whatever it is to increase resilience? Lack of funding, obviously, and then discordant policy signals. Obviously a big hazard as well. So actually, time-wise, sort of right around where I wanted to be. I just have 2 more slides. A couple sort of key points, maybe take-home messages from the talk, and then some ideas for where we might go with some of the future work. So the key point, I think, from my perspective, remains that small shifts in average conditions, which we tend to have more confidence about than we do about how extremes are going to change. Not always, but generally. Small shifts in averages can lead to large changes in the frequency of extreme events. Right? That's the sea level rise, coastal flooding example. It's transformative for many places. Doesn't mean you shouldn't try to say how will the storms change, but in some case it may be a second order question, or you may already have enough information to start an adaptation process, even before some of the science advances as much as we'd like it to about extremes. I say here we can't quantify how certain types of extremes may change. We can try to quantify if we make a certain set of assumptions, but there's just fundamental limitations to where we are, especially with a lot of these types of extremes. If we try to present in a quantitative way, we can move the science forward by saying, here are the assumptions we make. We're looking at a recent extreme event. These are the ways we're going to assess it. We're going to use these climate models, but we need to simultaneously, articulate the limitations and the uncertainties associated with each of the tools we're using in the assessment if we want to truly try to make a probabilistic statement. So I think that's okay. I think a lot of decision makers aren't asking for precise probabilistic projections of how extremes are going to change. But what can we say in a qualitative way that's helpful? And can we point to where we think some of the biggest scientific advances are likely to be in the future, where we might want to see money invested in ways that could improve the science, could improve the tracking of key indicators associated with extremes. As I said earlier, some of these events are so rare, it's really hard to know their baseline risk separate from the climate change question. Their multifaceted nature adds complexity. How will different drivers interact? Very high potential for surprises with extremes and emerging behavior that isn't even sort of present in the climate to date or in the climate models that we use. Okay, so you sort of come back to sort of the part of that first point in a way, focusing on areas that have a high vulnerability now, and just asking, is that risk likely to go up or down? Is there potentially a big enough change in the risk that you want to reassess how you're thinking about some of your big investments and protecting them, things especially that have long lifetimes. Okay, so. Some of the ways that we're moving forward and that others are moving forward, and as I say, we would love to, excited to collaborate on some of this. Going further with this sort of joint hazard approach, if we think about flooding, so I talked about our study where we looked at sea level rise and how one piece of storms might change, hurricanes. There's a lot of research here at Columbia and in the region about how nor'easters might change. You'd want to bring that piece in as well. And at least as important, where are we in this sort of combined effects of the heavy rain events with the coastal flooding and the sea level rise? They can all interact in low-lying areas. As you have more sea level rise, it's going to be, if you just have the same rain events you've had in the past, it's going to be much harder for that water to make its way out in all these gravity-fed systems. Of course, a lot of times when we're having a big storm surge, we're also having heavy rain events. That wasn't so much the case in our region with Sandy, but if we go back and look at a lot of the storms in the past, those two things tend to go together. They tend to be correlated, right? So we can't just think about each of those three risks, sea level rise, storm surge, heavy rain. We need to think about their correlation in time across models. And there's, depending on the shape of that coastline, there's huge nonlinearities that are possible. Places like Hoboken, with just a little bit of sea level rise, are going to have a really hard time dealing with rain events. So temporal and spatial correlation of extremes. So the temporal example here, if we do see a setup in the future, which is very, the science isn't in yet, but if we do see more of the types of troughs setting up over the East Coast that there have been a lot of in recent years, that is going to may tend to give you a pattern where certain cities are sort of in line to get more nor'easters than they typically would, sequences of nor'easters every 5 days, every week. The science is not in on that either, but you could make the case that if you're Boston thinking about long-term planning, do you want to start to ask whether there could be some forecast products that might tell you a month in advance if you seem to be setting up in an atmospheric pattern that might tend to give you a setup that's giving you more nor'easters, for example? What are the implications from an impact perspective of having, if the hurricane, this is speculative, if the hurricane season in the Northeast were to expand, if you started to get more hurricanes earlier in the summer, when you tend to have more heat waves, we may be underestimating that risk of the power going out at a time when you can have a really hot event right after it. At the other end of the spectrum, if the hurricane season were to expand, arguably that might increase the risk of extratropical interaction with cold air systems coming down from the north in November, December. Is there more potential for some of those Vermont 1927 types of just incredible rain events due to interactions of different types of extremes sequentially? Evaluating these potential adaptation strategies in the context of rare extremes. You're trying to build a 1 in 100 year floodgate that'll protect you against a 1 in 50 year storm. Just due to bad luck alone, you could have a 1 in 1,000 year storm the next year. Scientifically, we can explain that, but that doesn't mean that decision makers are going to be able to convey that message. And by the same token, you might build an adaptation strategy that's not able to meet the goal that it sets, and just due to luck alone, it might not get tested. So, how can we stress test some of those adaptation strategies without having to wait for a 1 in 100 year event, which isn't, is not a useful timescale. Integrating different types of information into risk assessment. This is sort of getting back to that triangle. It's if you want to do a sea level rise projection, if you want to do a projection for a lot of these types of extreme events, there are some process-based elements that our models don't do well. arguably we should be going to expert elicitation for some of these pieces. What does the community of experts think is the most likely? It's not ideal, but it may be a more useful data point than any other that we have. How do we integrate that with some of the pieces that we think can be handled in a more quantitative way with models? Are there other communities we can look to? Nuclear industry that have, for example, that have experience sort of integrating these sort of qualitative process-based approaches with things like expert judgment, model-based outputs. I think we should think about that in the extreme event context too. And some of that correlation of risk also is not just across joint hazards, it's also across systems, right? The power is more likely to go out when you're having that extreme heat event. So as we're thinking about the risk piece, the human systems piece, we need to be looking at potential correlation there too. And then I guess sort of the final point I want to make is just that this, engaging with the stakeholders so early on in this process improves the science in huge ways. And as we think about this sort of going away from the model of what's the hazard, how's it going to change, what are the impacts, and how can we adapt, to really starting to say adaptation is underway in this region and other parts of the world. How can we sort of iterate back and how can climate science continue to, and advances in climate science continue to inform some of these decisions that are underway? And I think it's a new science. So that's all I got. 1 hour exactly, 20 seconds. So what time is it?
Great talk, Radley. Thanks a lot. So my question, it has to do with this issue of the probabilities determinations. And whether scientists like it or not, policymakers are still and always will be demanding some specifics when it comes to probabilities, because at the end of the day, the resources, which are to a certain extent a zero-sum game, not only the money resources, but the people, the energies, the focus, and so forth, has to be reined in a way that makes sense to a government, a city government, federal government, the UN, whatever it might be. So we keep getting pushed about, well, how likely is it actually that that this event will occur versus that event? That event might be something we've never seen before. Might be a meltdown at the Indian Point nuclear power plant, or it might be a pandemic that happens sort of out of the blue. And I think that this is, I simply don't have an answer to this, but I don't think the pressure will be relenting in terms of what politicians and policymakers, or the public for that matter, or the media, expect from science. So I think that I would love to hear your sense of what the dialogue should be like, so that we can actually understand and embrace their demand for probability, understanding that we can't necessarily deliver what they might want.
Yeah. So I think, there's a lot to unpack there. I think the demand is always going to be there. I think there's probably a way to point out that basically all those decision makers are already making decisions with tons of uncertainty about economic projections, basically everything. So we can try to frame our uncertainties in the context of some uncertainties they're used to, that they think about all the time. I think, I think there's value in the exercise of trying to arrive at a probabilistic projection, even if you're never going to completely be able to get there. We can get a little closer. We can really identify the assumptions that we're making. When we try to do a probabilistic projection, we can try to say, all right, if this projection were to fall apart, what do we think are the sort of 3 things that would be most likely to surprise us? Tracking each year whether there are any sort of signs of those surprises, right? It's very hard to track these things. It's very hard to say to what extent more recent rapid melting of land-based ice actually suggests we're going to have, an extreme sea level rise scenario. It's a data point. It increases the risk for sure, but when those actual numbers are still fairly small, it's not a sure thing. So, but it's something we should track. So we can, in a qualitative way, articulate. I think at the end of the day, you sort of arrive at IPCC type approaches often of We think this is more likely than not. We think this is very likely. It's not ideal, but I don't really have any more insights than that. I guess the cliche I would say is like, oftentimes I think the 2-page tear sheet with the numbers, most likely projections, is less valuable than the supporting report. But
Just a quick response to that,
Yeah.
and not to make your life more complicated, but well, all of us work in certain silos of our own expertise, our science, or evidence. So you might produce what you just said within your silo, and then there's 15 other silos. I mean, the federal government has 15 major disaster planning scenarios. So the probabilistic estimates or calculations or whatever it is that you want to create for your field are confronting those of the anti-terrorism guys, for instance. So there has to be, there really is no framework right now for the overarching assessment of high consequence event frequency or probabilities. There's no such mechanism right now. So it leaves the mayor or the governor or the White House, for instance, grappling with how do I say what this table of climate experts is saying against the other table of the seismologists or whatever are saying. So just a point, maybe rhetorical.
And a lot of those uncertainties will cascade as we start to put those systems together. Do we want to try to identify consistent assumptions? Do we want to have consistent scenarios? If a climate projection is based on an assumption of rapid economic growth, how does that align with the assessment of vulnerability to climate, for example? So consistent scenarios. Other points. Other questions, comments? I think there's a mic. Oh, does Erwin have? Oh, yeah.
Great, thanks. So we're hearing Jeff Sachs and a lot of climatologists talk about this 2 degrees Celsius threshold, that's sort of the point of no return in terms of a lot of the extreme scenarios that you described. And we also know that like fossil fuel companies, if they were to burn even a third of their reserves, we'd pass that 2 degrees Celsius threshold. So sort of linked to Erwin's question, what do you see as your advocacy role, if any, on the more prevention-oriented side, that there's actually a lot we can do if we keep these fossil fuels in the ground to prevent or mitigate some of the pretty horrifying, regardless of probability scenarios that you're describing?
Yeah, and even if we can't, there's if there's I think we have to keep in mind how much uncertainty there is around these statements about we'll be okay with 2 degrees. What does that even mean when we know that there are so many populations, so many islands that long-term, low-lying populations that we can probably pretty much assume that 2 degrees Celsius isn't going to protect. We're learning more and more in some systems about, separate from the climate piece, how much more vulnerable our systems are to a little bit of warming, right? So we talk about a little bit of increase in average temperature increases the frequency of high temperatures. We're also learning that just a little bit higher temperatures in places where there's not a lot of variance throughout the year in high temperatures can lead to much more crop exposure, for example. Some of the literature here, trying to tease out some of the human vulnerabilities, risk of conflict. So, my personal feeling is that we're probably underestimating the risk of climate surprises at 2C and almost certainly underestimating the risk of sort of impact and system surprises. But on the other hand, I do think there's something to be said for encouraging and acknowledging that there are some signs of progress. We're nowhere near on the track that we probably need to be, but we are maybe increasing the chances of from very low to a little higher of sort of having a chance to get on a different emissions trajectory. I think I really answered the question, but I think we need to keep in mind that I think the 2 degrees Celsius is somewhat arbitrary, but still very helpful, maybe would be the way to put it. But we don't want to, put more confidence on it than it is.
Thanks for that talk. So I was wondering how you reconcile the spatial differences in the level at which we need to make decisions with the spatial scale that we can provide these decisions or provide information. Like the climate models don't give you information at the scale of New York City.
Mm-hmm.
And so how do you try to provide information to these decision makers who want information at that spatial scale? And then also, like, from your experience, can you say something about how we should be moving forward in the climate modeling community to in the future efforts for like these integrated climate model assessments? Yeah. And like what should we be pushing forward in terms of the climate modeling aspects?
Yeah. So a lot of great comments there. I mean, I think from my perspective, part of why I'm highlighting this point about how shifts in average conditions can have a big impact on the frequency of extremes is because it's much harder to assess how those really extreme events are going to change. I mean, if you look at climate model projections for how average temperatures are going to change across the Northeast U.S., there's very little variation in different regions. Now, you can make a case that right along the coast, climate models are probably going to get it wrong. I would probably push back and say, yeah, maybe right along the coast, we expect a degree less warming than we would further inland. But if you're talking about shifting averages, those are probably going to be second-order differences. But I think as we push further into how are the extremes going to change, that hottest day per year, we have to be more open to the idea that local scale dynamics could really matter. The sea breeze might actually be a lot stronger, might become more of an issue on those really hot days. So I would say that the spatial resolution issue certainly becomes more important, without question, as we go further and further into extremes. But I still tend to think that there's a lot we can say about extremes. And I think we underestimate in some cases sort of how the large-scale forcing could change in ways that impact regions. We probably also underestimate how vulnerable a city is to the impacts of climate changes over a much bigger region. So this is sort of my personal philosophy. My first place to look isn't sort of more downscaling or finer resolution. I think it's very helpful, but I feel like there's a lot at the large scale that we don't understand. Certainly we want to be pushing further with high resolution regional climate modeling, for example, but how far are we from being able to get long enough ensembles driven by enough GCMs to help us? It's one of the areas we need to push in. And as we talk about testing adaptation strategies, high-resolution models are going to be more important, right? As we start to ask, what impact does planting 1 million trees have on neighborhood-level temperatures? What impact does more white roofs have on temperatures? So I think we'll see regional models used more and more for testing adaptations. So my personal perspective is that there's still a lot we can say for cities about changing risk, even though there are inherent issues of spatial scale.
Thanks, Haley. When we think about risks and probabilities, there's sort of two kinds of uncertainties. I mean, the notion of risk is that there's something we can't predict exactly what's going to happen because the weather's too far in the future, but we know there's some distribution, and so we talk about risk, that there's a 1% chance or whatever. That's there even for a known climate, whether static or changing, but as long as it's known. Then there's scientific uncertainty, right, that we just don't know the climate sensitivity or what the greenhouse emissions are going to be or the rate of sea level rise. Is there anybody thinking in a concrete way about how to reconcile those? And to give a concrete example that you probably know more about than I do, I've observed it only from a distance, the FEMA flood maps, for example, what's a 100-year and what's a 500-year flood zone, as I understand it, the engineers have ways of doing that based on looking at the past data and extrapolating with extreme value theory, whatever. But then if you want to add sea level rise, which FEMA hasn't done as far as I know, my understanding is not that they don't believe in sea level rise, but that you either have to choose a scenario, which nobody really wants to have to do, or you have to have some way of building in the fact that it's not even just different climate models, it goes beyond the climate models, the ice sheets are not yet fully integrated, so it's another whole level of uncertainty. And my impression is they haven't done it because that's totally different than the kind of information they're used to dealing with, and the engineers just don't know how to integrate that. So that's a very practical level, but even on the broader sort of policy level that Erwin raised, I mean, how do we think about these two things at the same time?
Yeah. No, I think that's extension of the really, as you say, the really challenging question from Erwin. And I think I agree that the engineering community tends to be a community that understandably wants a number, is less comfortable with these sort of flexible approaches. And maybe at some point you make a set of assumptions and you just sort of move forward with that. You have, for the last National Climate Assessment, there was a sea level rise task force that basically came up with scenarios. And they didn't try to put a probability on them, but they did try to sort of describe some of the characteristics that they think would go with the sort of 4-foot scenario or the 2-foot scenario. Gives you a little more information as you ultimately sort of have to step into your risk comfortability, right? Because that's the other sort of half of this. Is even if you knew the science piece perfectly, there'd still be the question of your risk profile and sort of where you are. But I don't have an answer to it. I think it's a huge issue. I mean, to some extent, I guess the easy answer with FEMA which is the challenging answer, is they're not allowed to, right, to look at sea level rise in some sense. But even if they were, or when they are allowed to, there's going to be this sort of huge step of what numbers do you use. I wish I had a better answer.
Thank you. Well, I would think that there is an answer to Adam's question. What is happening in the ideal world, in which we would have perfectly described scientific uncertainty, meaning that we would have a distribution, we would know what is the distribution of possible climate scenario. And in which each scenario we have complete scientific understanding of what risks are, then that is what Bayesian would call a hierarchical distribution. You would multiply this to probability and integrate overall scenarios. That's it. So all you need, Adam, is to improve the quality of knowledge on both these elements. But it's good to break things in two.
But you need the consequences too, right?
Well, you started that we have a distribution for, well, which one? You don't have risk, or you don't have possibilities?
Possibility. I think for sea level, I don't think you could get the experts to agree on what the PDF is and possible sea level.
Yeah. There have been some efforts in that direction, but they're certainly not there at agreement. But people are trying.
Right. I also had a question. In half of the time, you are using the words extreme events in a sense of disasters, I think. And I wonder if it's a standard vernacular now, or we should be a bit more precise here, because these are not the same thing. And moreover, half of understanding of reasons for disasters is connecting them to the proper extremes. And sometimes these extremes are awfully unusual climate extremes, like in case of Sandy, probably distance of the epicenter to the New York City was the most important extreme.
Yeah, and just the bad luck of it hitting right at the normal high tide cycle, and a lot of how much of a disaster it is depend. There was this heavy rain event in New York City in 2007, August of 2008, shut down the subway system, and a lot of that was just the bad luck that it had such a devastating impact because it happened right at rush hour. Just something as arbitrary as the impact depends on time of day, time of season. If you have a really heavy rain event during that period when you have all the leaves on the ground, you have much more of a flood risk. There are these, I think, and that's a place where obviously, working with the decision makers more is a big help. And I think you can, one thing you can do is sort of invert the process. Instead of saying, let's define the most extreme events from a climate perspective by how rare they are, we could start with decision makers and say, what are the systems that impacted you the most? What are the events that impacted you the most? What was the climate piece? And maybe there's ways to move forward there in identifying some of this. But yeah, no, you're right. Obviously, the different vulnerability among different communities as well is a huge piece. The same weather event can be a disaster for a less prepared community than for another. I'll plug a new paper that Corey has in Nature, I think, out just about any day, where they started from disaster definitions in looking at impacts rather than weather-defined climate extremes. So we can send that around when it's out.
Yes, hi. I was wondering if you could comment a little further regarding the probability of the frequency and intensity of hurricanes and how that relates to climate change.
So basically, what do we project for how hurricanes may change in the future?
Yes.
Okay. So, yeah, and I think others should weigh in on this one as well. I'd say that probably at this point, the balance of evidence still suggests that the strongest hurricanes will become a little more frequent and stronger. It's not a sure thing, but overall, the thinking is that especially sort of as the upper oceans warm, as you have more moisture in the atmosphere, it's easier to get some really big and really powerful hurricanes. Not a sure thing, but that's sort of what the balance of evidence suggests. If we look at historical trends, probably over the majority of the world ocean, there's no clear upward trend, certainly in the frequency of hurricanes. Maybe the Atlantic is an exception, but in most places there isn't. And in most of them, there's not an upward trend that's, significant trend in the strongest storms either. Of course, that's trickier, right, because they're rare. We have natural variability, we have change in aerosols. So the historical trends don't tell us a lot. Theory seems to suggest that probably the strongest storms will become stronger, but there's tons of other pieces we have to think about besides the upper ocean temperatures. What's going to happen to wind shear in various places? What's going to happen to stability in the atmosphere? What's going to happen to not just the temperature profile in the atmosphere, the moisture profile? What's going to happen to aerosols, dust? So I don't know. Adam, what do you think? I'd say the balance of evidence suggests the strongest hurricanes become stronger, but not a sure thing, and the verdict's very much out on how the number of hurricanes will change. Probably more heavy rain events also in more heavier rain. Yeah.
Building on that question, is Hurricane Patricia an example of anything? Is there anything the media should have learned or the corporate environment should be looking to it for, like we do with Sandy?
So I think one thing that I would highlight, sort of separate from the climate change issue, is a lot of these recent events that have gotten so much attention are getting us thinking more and more about, we shouldn't just be thinking about the strength of the winds or the central pressure in these storms, right? If we look at, one of the things that made Sandy so devastating, it wasn't just the surge due to the coastal flooding due to the fact that it hit at high tide. It was also the size of the storm, got so much of the ocean spinning. It's the same thing with, I think it was Ike in the Gulf of Mexico. The winds weren't that strong, but it was such a big storm that it basically got a lot of the northern Gulf of Mexico spinning. So size of the storms matters a lot. Patricia was a very small storm, incredibly strong winds, but the spatial size was small. If a community had a populated area, had been unlucky enough to be in the right spot or the wrong spot to get those really heavy winds, it would have been devastating. But the fact that it wasn't a very big storm spatially made the exact track of where the storm went much more important, reduced the amount of storm surge, and reduced the number of people exposed to strong winds. Because from the wind perspective, it's that area with the really heavy winds that, goes, I think, as the damage goes, is like the cube of the wind speed. So it really, really matters who's getting the heaviest of winds. In general, I can't weigh in on the attribution. I mean, I think it's telling that we're seeing Wilma, this storm, strengthening very quickly, going from basically Category 1 to Category 5. But we don't have a real long record of storms over the ocean in the past, so it's hard to link to climate change. But one thing a lot of these storms have had in common is very warm upper ocean temperatures. But again, linking that to climate change isn't easy. They're individual storms. And upper ocean temperatures are just one of the factors that affect them.
Hello, thank you. It's a question from a beginner.
Say again?
It's a question from a beginner in terms of risk management. Is the following approach being investigated? Not thinking in terms of the response we might have in case of an extreme event in New York City or whatever, but working more broadly on the resilience of the whole system in case of anything happening, no matter it's a flood, a hurricane, earthquake, but just the resilience, the global resilience of the system as a whole.
Yeah, I mean, that's a great question. I think there are initiatives focused on that. Others in the room probably could speak much more to it, but strengthening infrastructure, investing in infrastructure, which is, a state of total neglect, in the U.S. and much of the world. It protects you against, all sorts of types of risks. Doing anything to have more fail-safe systems, backup power sources, cooling centers people can go to, increasing public awareness about vulnerability, getting messages out to look out for the most vulnerable members of your community. I had one other thought on that. It'll come back to me. Poverty reduction, right? Just anything to sort of protect baseline health, access to opportunities among the most vulnerable communities is going to help against all types of extremes, including non-climate extremes. It's not always, yeah. It sort of is that simple. Yeah.
Thanks. Hi. My question actually relates to kind of things that are occurring on the surface, so namely, say, land cover changes. Mm-hmm. And I was just wondering, as far as, given all the kind of the lines of evidence that you've presented and different models have been used, I mean, is there also like an infrastructure base model that we could consider as far as, changes of infrastructure in respect to time will also offer this potential offset or this potential change?
Right. So I think we need more integrated modeling of that type that tries to ensure consistency across, say, these scenarios of a world with higher greenhouse gas concentrations. How would the vulnerability change? But I mean, most fundamentally, these climate models are being run with a just sort of set of assumptions about what future greenhouse gas concentrations, or what we call sort of the forcing of the atmosphere, is going to be. They're not really run in a coupled way. With land cover, that's changing. Some of the models do include interactive land cover, where a temperature change can change forest cover in a way that can sort of feed back on moisture fluxes. But in general, in a way, it sort of gets back to Erwin's point, I think, as we're sort of doing risk assessment to try to have consistent scenarios. And just like we're thinking about greenhouse gas emissions averted, what could that mean for reduced vulnerability? What could infrastructure investments mean for reduced vulnerability? And making sure they're done in a way that doesn't make them more vulnerable to changing climate.
So I was just thinking that the other side of the issue of extremes, when you go to the users, to the stakeholders, one of them is to prepare and create defenses against the upcoming extreme. But the other side is disaster preparedness. Something hits and you could not avoid it. Right. How to do the best thing to avoid a disaster. And Erwin can probably talk a lot about that, but I think that the role of the climate scientist is also to prepare the people who are thinking about avoiding disaster once it happens.
Yeah.
And that's sort of like a different role than giving statistics about possible extreme events. That goes more towards scenarios or something of that sort. Can you say something about that?
Yeah, I'm not sure if this is exactly the examples you mean, but we could set up sort of plausible outcomes. If a hurricane were to be coming towards New York, how soon in advance, or any city, how soon in advance might you have wind speeds that would shut down your bridges, making evacuations more difficult? What's a plausible set of things that could happen? What are the odds that you'd get that hurricane occurring and having a heat wave right after it? That sort of thing. Is that sort of what you're thinking?
I was even thinking more about that we have within the Earth Institute, for example. Yeah. We have the possibility of thinking also about this kind of aspect. Not only the infrastructure building to avoid extreme, but also, something happens. How the best to handle avoiding a really social disaster.
Yeah, absolutely. Absolutely. Yeah, what can you plan in advance? What sort of backup networks can be in place? Can we identify vulnerable populations beforehand? Think about how to avoid taking preventive strategies, moving people that, if not done right, could cause more harm than good.
It's wonderful listening to you. The climate science which you have talked is more of top-down approach.
Yeah.
Why there is not much gearing from the bottom-up approach? In other words, to say science-policy interaction, why not it is science, society, and policy interaction?
So maybe that's like going for a little less technocratic approach of sort of how is this infrastructure going to be affected by it? I mean, I think it's bottom up in the sense that, so if we go back to like the New York City example from the early 2000s, it was bottom up in the sense that it started with decision makers, but it was somewhat of maybe a technocratic sort of infrastructure-based approach. What's going to happen to the transportation systems? What's going to happen to telecommunications? So I think what you're saying, if I'm hearing you right, is having a broader set of voices sort of weighing in on visioning, for what a positive future looks like. So it's not just adapting to reduce climate risk, but how do we want the city of the future to look in a much broader definition of quality of life? Is that sort of where you're going?
Involving the local communities.
Yes. So so I would say that wasn't a huge feature of New York City's approach to circa 2007, 2008. But I think that's changing now to some extent. I don't know all the details, but my sense is that there are sort of some community outreaches where these Plan YC or 1YC is being vetted. So I think there's more of that. I think certainly environmental justice organizations, for example, have much more of a seat at the table than 7 or 8 years ago. There's probably a lot more that can be done in that respect, but I think it's at least trending a little in that direction. Yeah. It's a huge issue when we think about adaptation strategies too, making sure that they benefit all members of society and don't have sort of perverse effects that harm some of the most vulnerable communities, changing real estate values or whatever it might be, increasing flood risk outside of a protected area. Adaptation Futures. Yeah. So Adaptation Futures is a once every 2-year event, very much focused on this issue of sort of the emerging science of what adaptations are underway around the world, practitioners talking about their experiences in the adaptation space. And it is in the Netherlands. No?
Go ahead, but I meant ours, so go ahead.
Oh, yes, right. Okay, so this is an every 2 years conference in the Netherlands in May, I believe. But yes, we have, actually, come up and say more about it. There's Jesse Keenan's group, which is the real estate, having a real estate conference on December 3rd.
I'm in August.
Okay, so there's so much happening at Columbia and in the broader community.
There's a conference on, there's a lot of conferences on adaptation. And Jesse Keenan's involved in 2.
Okay.
But
pick up the mic.
But I was thinking of the one that, because Radley and I are both on the committee, I thought that we would know.
Sure.
But as long as people are here, it's next August, and it's a UN thing. It's a UN, Northeast U.S. Climate Adaptation Conference. So this is a UN organized thing, but it has to have a host place. And because of Jesse Keenan, who's at Center for Urban Real Estate in the Graduate School of Architecture, Planning, and Preservation here at Columbia, they put in a bid in to be the host, and we are the host. So this is next August, like 16 or something. It's like a 3-day long thing. And so for anybody who's interested in adaptation, there's lots and lots of time to sign up or submit an abstract or do all of that. But you can find it at certainly on GSAP's webpage or on ours, extremeweather.columbia.edu. I think Haley made it one of the front pages that you see. So if anybody's, it's very relevant to what. There's also the one in the Netherlands, and there's also the one in. There's a 1-day thing at GSAP on December 4, which probably is open, but
I think so. Great, thanks. Lisa? Oh, here, let me. Yikes.
I was just wondering if you think that the MPCC model will be adopted by other cities in the United States and around the world more and more in the future, because it's something very unique that was developed in the city. And one of the concepts that Cynthia is very frequently talking about is that cities are taking the lead in climate adaptation, and there is so much more that can be accomplished this way. So I'm just curious about your thoughts. How likely is it that more and more cities adopt this kind of integrated approach?
Yeah. So my perspective is that it's happening. I think we're really seeing this non-traditional actors sort of going beyond the nation states, more and more emphasis on greenhouse gas emissions reductions and adaptation, private sector, community groups. So I think we're seeing that more and more cities getting engaged. And I think it doesn't hurt that the climate dialogue is moving front and center so much. It's arguably we're getting sort of closer to a point where there's really an expectation of not only disclosing greenhouse gas emissions, but also potential exposure to climate hazards and climate change. I think as we see that becoming more and more just the expectation, from a fiduciary perspective or whatever, cities are essentially, more and more going to be kind of required to think about these things. There's still the issue of how they do it, and I think the NPCC model, New York City model, with this iterative approach and sort of thinking about how to keep track of indicators, how to keep track not just of the changing climate science, but what's becoming feasible in terms of adaptations, or costs coming down, or how are impacts changing, right? Are more people moving to or away from the coast? These iterative approaches, I think, are going to become more and more common. Probably already are. And now there's so many other cities that also are kind of leading globally. So I think, I think we're seeing more, C40, some of those kind of groups. So it's happening. But probably it's just as important to note all the cities that don't have the funding to do their own assessments, all the smaller towns and municipalities. So I don't mean to suggest that there's not, still a lot of need, but maybe it's kind of moving in that direction. Yeah.
Let's say the last one.
So my question comes more from the lens of insurance companies and the insurance market. So we've dealt with a lot of clients and insurance companies and brokers who are really interested in how climate change is going to affect property insurance. Mm-hmm. And I was thinking, when you were describing the wet bulb temperature study in terms of heat waves and kind of human exposure, do you see an opening in the market or kind of an expanding space where more life insurance companies could kind of make policies for that sort of thing?
It's a good question. I honestly hadn't thought about that. I mean, I think it's a grossly underestimated risk. I mean, I think it's a big if whether these projections that I showed are going to, there's still a lot of uncertainties there. But if we see some of the things that I showed, it suggests that in some low-lying regions, people could be thinking as much about heat stress as about sea level rise, which I don't think is an appreciated thing right now. So that would tend to point towards at least the idea that it could go on people's radars more. Then you think about correlation with air quality issues. Think about the odds of the power going out. Think about outdoor workers. So there's there's a lot of big issues. A lot of the earliest thinking about heat stress, I'll say, was risk management in the military, Army, sports-related things. So there's some people have been thinking about this, but I think not really in the climate change context yet is what makes it. It's changing, but it's changing like in the last year or two. So that'd be an interesting thing to look at.
Okay, thanks, Radley, and thanks everybody for coming, and we'll see you next time.
Thank you.